All right, in this lecture, we're going to talk about the differential form of Gauss's law. So in order to start and get an understanding of this, we have to think a little bit about what's called the fundamental theorem of calculus, which I'm sure is somewhat familiar to you guys in the back of your brain somewhere. Okay, so what I'm going to draw here is some function. Okay, and we'll call this function something real general, like f of x, and this will be x. Okay. And if you guys remember the fundamental theorem of calculus, if I just write it down, the fundamental theorem of calculus states, right, that if I do an integral between the limits of a and b of a derivative of the function f with respect to x, and I do the integral with respect to x, that's going to be equal to that function evaluated at the limit, okay? If you just look at this and you've done a lot of integrals, you're kind of like, duh, of course, right? I know how to do that integral. But we want to think a little bit more about what this means, okay? So remember, this is like the rate of change or the slope of the function. That's what that derivative represents. This is the size of the step. And we're going to take tiny steps, right, because we're doing an integral. And these define the start and end points, right? That's what the limits define. Okay, so what I'm doing here when I'm taking this integral is I'm doing an integral, but what I'm really doing is an infinitesimal sum. So if I want to start here at A and go maybe up to here at B, what I'm doing with the function is I'm evaluating the slope here, and I'm using that slope to tell me how to take a little step. And when I do that, what I'm really doing is I'm kind of building what the function really looks like out of these little steps. So when the book talks about measuring stairs, okay, it's a good analogy. If I want to figure out how tall the set of stairs are, I'm going to make this be a little bit lower so my job is a little bit easier. That one. Okay, so if you're measuring a set of stairs, you could either go and measure each individual stair in order to figure out how high the stairs are, or you could just figure out the elevation of the top stair and the elevation of the bottom stair and just subtract them. So this side of my fundamental theorem of calculus says, hey, go ahead and measure each of those stairs. The right-hand side says, yeah, it'd be easier if you just took the difference of the function between the endpoints. Okay. All right. So hopefully that makes a little bit sense. We're going to start with this idea, but we're going to apply it to more than one dimension. Okay. And so let's think about taking a sum. Of course, we're really going to think about an integral, or doing integration of the divergence, which, if you guys remember, is something like flux per volume, but it's evaluated at a point in space. It's just a way to think about it. Okay, we're going to do this over a volume. Okay, so I want to take the sum of this divergence, this idea of flux per unit volume, over a volume. So what that's going to look like in terms of an integral, okay, it's going to be a volume integral of the divergence, which I can calculate of a general vector field V this way, okay, where d tau, if you guys remember, that's our infinitesimal volume. When I'm doing this, what I'm really trying to figure out, okay, is how much of that volume is a source or a sink of flux, okay? So as I integrate over a volume, scan over it with my integral, I'm looking and summing all the sources and sinks of flux. So you could also think of it in terms of a light analogy. You can think about, as you go over your volume, how many light bulbs do you find? Okay, when we think about electric field, how many charges do you find? Okay, it should make sense that if you integrate over this volume, looking for sources and sinks of flux, that what you find should be directly related to the flux across a closed surface. So this quantity is directly related to the flux across the closed, okay, it's got to be closed surface of that. And by that, I mean the actual volume you're doing the integral over. Okay, so if I think about doing this integral, the result's going to be related to the flux at the surface of the volume that I did the integral over. Okay, so this idea is got a few different names. Okay, this idea is called, depending on who's in favor at the moment, could be Gauss's theorem. Sometimes it's called Green's theorem. Sometimes it's called the divergence theorem. Okay, it's got different names, but the idea is the same. So this is the flux across that closed surface. Gauss's law tells us that flux is equal to actually evaluating that vector field at the surface, so taking the dot product of the vector field at all of the elements of the closed surface. But the divergence theorem tells us that that's also equal to evaluating the divergence of that particular vector field over the whole volume. Okay, cool. Let's apply this to Gauss's law. Okay, so I'm just going to replace that general vector field with the electric field. Okay. And Gauss's law tells me that's related to the enclosed charge over epsilon naught. I'm going to get rid of that middle bit, and I'm just going to say, all right, that means that our volume integral of the divergence of the electric field is equal to the enclosed charge over epsilon naught. Okay, let's think about how we can define our enclosed charge. So we're going to calculate our enclosed charge by summing or integrating rho, which if you guys remember is our charge per unit volume. Okay, so that means that I can calculate the enclosed charge in a volume that's described by rho, some charge per unit volume. Doesn't have to be constant. It could depend on the actual position within the volume. Okay, but I can define it like that generally. And let me go ahead and rewrite that then. So now I've got the volume integral. Oops. So now I have the volume integral of my divergence, and that is going to be equal to the volume integral of now rho over epsilon naught. Okay, since I'm integrating over the same volume, so d tau is the same for each of these. Okay, this gives me this particular relationship. The integrands here have to be equal. So what we end up with is what is called the differential form of Gauss's law, okay? And that says, right, that the divergence of the electric field is equal to our charge density divided by epsilon naught, okay? So we can use this to relate the divergence at of E at a point, okay, to the volume charge density at that point, okay? So if there is no charge at that point, then the divergence has to be 0. But if there is a certain amount of charge density at a point, okay, then that divided by epsilon naught is going to be the same as the divergence of the electric field. And this, by the way, is what is done in problem, we want an example of this, 2.9.